Next, we're going to look at the use of the binary heap data structure to implement a clever sorting algorithm known as Heapsort. So here's the basic plan. What we're going to do is we have our n keys, and we'll have them in an array. We'll view that array as eventually being a max heap. So what we have to do first is to rearrange the keys in the array to heap order it. So just make it so that every key is larger than its two children. And for example, the largest of all the keys is at the root. And then the next phase would be to take that heap ordered array and get it to be a sorted result in place. And again, the heap is stored in the array with the first key position 1, next to position 2 and 3, and like that. So the end result would be like that with no keys in the heap, but all the keys in the array in sorted order. So it's a little exercise in abstraction. Part of the array is the heap, part of the array is the sorted subarray, and eventually we bring it down to the whole thing being sorted. There's very little code beyond the basic heap code that we've looked at can get this implemented. That's called Heapsort. Let's take a demo of how Heapsort works in our example. So the idea is we're going to use a bottom-up method. So all that means is we start with an array in arbitrary order, and then we're going to work from the bottom up to make sure that it's heap ordered. Well, all the nodes with no children are heap ordered. They're only of size 1. The first one we have to worry about is this one here. The root we haven't examined yet. Its children are heap ordered, so it's a small heap of size 3 that may not be heap ordered. In this case, it's not, because one of the children is larger. So that's where things are going to start. We have a lot of one-node heaps. And then we're going to have to perform the sync operation on this one at node 5. That's, in this case, just exchange it with this parent. And then proceeding in that way, moving bottom up or moving from right to left, the next thing we do is, then we have a 3-node heap that's heap ordered, and we're fine. Now we'll move over to the T, and again, that's the root of a 3-node heap that's heap ordered except at the root. And we may need to fix it with the sync operation. In this case, nothing is required because it's larger than its children, so we have a 3-node heap. And then we move one more to the left. Now we're looking at the R. Again, root of a 3-node heap may or may not be heap ordered. We do have to do the sync operation. In this case, that brings the X up. 3-node heap. Now we go to 2. Now that's the root of a 7-node heap. We know the 2 3-node heaps that are children are heap ordered, but we may have to correct the heap ordering at the root, so we do a sync on 2. And that's going to involve exchanging with the T, because T is larger than O, and exchanging with the P, because P is larger than O. Now that heap is a 7-node heap that's all heap ordered. And then the last thing is to do the root of the whole thing. And again, now the 2 subtrees are heap ordered. That's what we mean by bottom up. We took care of the heap ordering from the bottom up. And so we'll do a sync on the S and bring it into heap ordering. So that's with just a few exchanges, we got that whole array heap ordered. And now what we want to do is take advantage of the heap ordering in the array to do a sort. And the concept is very simple. Right away, we have the maximum element in the array right at the root. We want that to be at the end, so that's what we're going to do, is just put it at the end. We exchange the element at the root with the last element, pull it off the heap, and then that's our example. We might have violated the heap order condition at the heap right now, so now we have to do a sync operation on the E. And so it's larger than it's both children, and the larger of the 2 children is T, so we promote the T. And the P is larger of the 2 children, promote that. And then finally the E comes down to the bottom. So now that's one step in the sort. We got the largest element off. Now the next largest element in the array is now at the root of the heap. So we're going to do the same thing, exchange it with the last element in the heap. Then now the T is in its final position in the sorted array. We take it off the heap. So now we've got a heap with 9 elements, and 2 of the elements in the array are already in their final position. And now this one's not heap ordered, so we have to exchange it with the largest of its 2 children. In this case, that involves promoting the S and the R. Now it's heap ordered. So that's the end of 2 steps in heap sort. And then we just keep going, pulling off the largest element from the heap, exchanging it with the element in the heap in the largest position in the array, which brings that element into its final position in the sorted array, and then adjusting the heap ordering with the sync operation. So that E again is going to come down, and now it only goes down 1 step in this case. So now R exchanges with M, and it's in its final position. And you can see down at the bottom the large elements in the array filling in their final position. In the left part of the array is representing the heap. The R goes off the heap, do the sync operation on the M, and now we have a heap ordered array. So now do the P, exchange that with the A, take it off the heap, do the sync operation on the A. Now we're going to do the O, exchange that with the E, take it off the heap, do the sync operation on E, which involves promoting the larger of its 2 children until it gets to the bottom or a place where it's larger than both its children. So now we have just 5 elements left. We'll get the M, do heap ordering on the heap of 4, and that only involves 1 exchange. Now we get the L, A exchange with the larger of its 2 children. Well, they're both the same, so it goes with the left one. That's a heap of size 3. Pull off the first E. It's already heap ordered. Pull off that E. And now we're left with only 1 element in the heap, and it's in the first position, so there's nothing to do. So with a series of N exchange and then sync operations, we pull the sorted array out of the heap. Okay, this slide summarizes the code for heap construction, and as you can see, it's a one-liner. We go backwards through the heap, starting at n over 2, because the n over half of the rightmost half of the array is just little heaps of size 1. We just go backwards doing a sync starting at k. So that's the first piece of code for heap ordering an array with arbitrary values. And then these diagrams summarize the sync calls that we just went through in the demo, starting at 5, 4, 3, 2, 1. As you can see, only 1, 2, 3, 4, 5 exchanges are needed to bring this into heap ordering. Then the second pass, again, that's only a 2-liner. We exchange the first element with the one at the end and then decrement the size of the heap, and then do sync operations. And these diagrams summarize the sync operations that we showed in the demo. On an ever smaller heap, we continue just performing sync operations at the root until we get a completely sorted array. Given the sync implementation, we had a 1-liner for the first pass and a 3-liner for the second pass. So that gives a complete implementation of heap sort with the code that we've given so far. There's one little detail. When you're sorting an array, of course, position 0 comes into account. And we've been building our heaps from position 1, but we can take care of that in the less and exchange methods by just decrementing the indices in those methods to have it work as if the array were 0 through n. And that's a little implementation detail, but otherwise this is a fine sort implementation that actually is very little code, and it's got a place in the theory of algorithms that I'll talk about in just a second. This is just another trace without the data structures shown to just show in our standard way the elements in black and red are the ones that are touched, and the elements in gray are the ones that are not touched at all. And to just show that this thing gets the sort done with touching relatively few elements. That's a trace. Let's look at an animation. Animation of Heapsort is interesting to watch. The construction of the heap happens in a blink, and now it's pulling off the largest elements moving from right to left. So again, a very efficient way to get a sorting job done. So what about the mathematical analysis? Mathematical analysis for the heap sort part is pretty easy. N times, we're doing a sync operation, and the size of the heap is at most log n, so it's n log n. The construction actually, it turns out, although it's a little more complicated to prove, that it always uses just a linear number of compares and exchanges. And that's an interesting result in itself. You can build a heap from n values in linear time. And then in n log n more time, you can sort from that heap. And that's significant because it's the first sorting algorithm that we've seen that is both in place and manages to get the sorting job done with guaranteed n log n compares. Merge sort doesn't do that. It takes linear extra space. Quicksort doesn't do that. It takes quadratic time in the worst case, even though we make that unlikely by random shuffling. It still takes quadratic time in the worst case. But Heapsort does both. Now there's more complicated versions of merge sort and quicksort that can do this in theory, but Heapsort is a pretty simple algorithm that gets both done. So if on a job interview somebody asks you what's an in-place sorting algorithm that's guaranteed n log n, your answer is going to be Heapsort. Now in practice, Heapsort's actually not used that much for a couple of reasons, and they might ask you these on your job interview too. First thing is the inner loop is longer than quicksorts. Like merge sort, there's more things to do in the inner loop. There's that compare the two children bigger, and then compare. So there's two compares that get done in n log n times, and then there's some that array index arithmetic. The other thing, which is probably more significant on modern machines, is that the references to memory are all over the place when it's a huge array. So it's not a good algorithm for a situation where there's caching, which is almost everywhere nowadays. It doesn't have local memory reference like quicksort does. It's always referring to something that's nearby something else that it just referred to. So if a big block of things comes into memory, there's no more extra cost. Whereas Heapsort is going to look far away from the current place as it goes down the tree, and that makes it slower in a lot of situations. And the other thing is it's not stable. Sometimes people choose to use merge sort in practice because of the stability, but Heapsort's not stable for the usual reason that it does long distance exchanges that might bring items that have equal keys back out of order. So that's our full summary of sorting algorithms. It completes our treatment of sorting algorithms with Heapsort. And this is just adding the Heapsort line to the table. It's in place. We don't use any auxiliary array. It's not stable, but its worst case guaranteed time is proportional to n log n, as well as the average and the best. This is not a trivial result, but it's also the case. So it's n log n guarantee in place, but it's not stable, and we still have the hope that someday somebody will develop a simple, in-place, stable, worst-case n log n algorithm, but we're not quite there yet. And that completes our treatment of sorting algorithms with the Heapsort algorithm.